right, we got a little bit of a special video here today. What I'm going to do in this video is I'm going to overview a technique called in-cylinder pressure transducer analysis. And yeah, that's a mouthful right there. This isn't going to be for everybody on the channel. This is going to be more for you guys that are way more advanced. I know I've got a lot of automotive students that watch this channel too. And this is going to help you guys and also the professionals that watch this channel, and maybe you want to consider getting into this. I know there's still a lot of professionals on the channel that watch me, and I know they don't even have a scope yet. Well, this may change your mind. So the real quick backstory here, I've been doing this for over a year, but I just don't really feature it on the channel because I never thought it really applied very much. Well, things are changing a little bit. First of all, once again, I have another car that had the parts cannon thrown at it. It has a misfire in a single cylinder, and compression test shows no issue. It had spark plugs replaced, coils replaced, fuel injector replaced, you know the whole drill. And I believe that there is a compression problem here. Now, we've been through this before with the head gasket that passes the compression test and everything. Well, this isn't a head gasket either. It's an intermittent compression problem that honestly only this technique is going to find, I believe. And we're going to actually show that case study over on my paid content channel at www.schrodingersboxqm.com. However, I'm going to overview the technique that we will use for that case study right here for you guys. Again, I've been using this for some time, and I've been getting more and more into it. And I got to tell you, this method it's just really, really powerful, and there's so much more to tap into with it. But I'm going to basically overview it. But the idea is by bringing it to you guys, it's going to provide some benefit. And also for you guys that are members over on my paid content channel, you will also be able to have a preview and further understand how I diagnose that car when it comes in this weekend. So the way I'm going to do this is, this will probably be a little bit of a longer video, but this is just so cool. And it really does have a lot of education value, even if you don't intend on doing this stuff. It'll really help you to understand the mechanisms of mechanical engine problems, which is basically what we're going to use this technology for, is when you've got mechanical engine problems, but a lot of your traditional tests either won't work, which happens more and more and more, or it's just going to be very time consuming because of accessibility of some of the engine components and doing a leak down test or stuff like that. Even then, the issue with the car that we're going to look at this weekend only happens when it's running. So you're not going to be able to see this issue most likely with a leak down test or with a compression test with it cranking. How are you going to see what mechanically is happening in a cylinder while the engine is running other than this method? So what we're going to do to show this is I'm going to draw an outline of what we're going to be looking at on the board, and then we will go to the car. We will pull actual waveforms under different conditions, and I'll show you how I analyze these waveforms to determine where an issue may or may not be in the car. You've seen me do this, actually a preview of this before, when I determined a valve lash issue on a Honda a while ago, and we were able to determine that using this technology. I'll put a link to that video as well. But there is so much more that you can do than just what I did in that particular video, and I'm going to show you a bunch of that stuff today. All right, little other project we're doing on the other channel. It also occurred to me there was another application we showed on this channel with the pressure transducer, and that was putting the pressure transducer on the radiator on a vehicle that, again, had a blown head gasket, had a compression loss issue, but it passed the compression test. It passed the relative compression test and the gauge compression test, but we were able to use this technology by putting a transducer on the radiator, and we could see that compression was indeed being lost through the radiator. It was just not at enough of a volume that could be detected through traditional methods. You can also put the transducer on the intake manifold and get data. You can put it on the exhaust manifold and get data. You can even put it on the oil dipstick tube and measure pressures in the crankcase and get data. There's just almost endless applications of this. We're just going to show the cylinder application for this, the transducer in cylinder pressure application. All right, so the first thing is, of course, you're going to need the oscilloscope for this. You won't need the picoscope, although this is what I'm going to use. I do have other oscilloscopes, but the picoscope is going to be great for the training purposes with the camera, with the high resolution and the ability to easily zoom in and get to specific details. But you will need to have an oscilloscope for this. The other thing you will need is an absolute pressure transducer. The oscilloscope, of course. The oscilloscope here is a 2-channel picoscope 4225 that was just an amazing donation from Robert Roble, one of my viewers on the channel. He goes by C5 Diag. He also has his own channel where he does a lot of Corvette troubleshooting and stuff, and he literally just gave this to me, and wow, just changed everything. Now, I made my own investment and I got this absolute pressure transducer. This is a picoscope, it's like a WX500, what is it called? WPS 500X is what this is. Now, this transducer itself was like $1,000. So there can be some very heavy investment in this. However, there are other transducers available online. I even know there are some people who have made their own transducers. I just got this one because I know that it's already pre-calibrated for my picoscope. Very durable, can use it with liquids and things like that. It also has really, really excellent sensitivity, although there are some out there that are even more sensitive than this. But this has zoom in capabilities to get really, really good sensitivity on minor changes even. You don't have to invest in this to do the technology I'm going to show you. You just need a basic oscilloscope and some kind of pressure transducer. Do keep in mind there are 2 types of pressure transducers. You will have your absolute pressure transducers like this one. There are also delta pressure transducers. The difference, real briefly, I don't want to go into it too much, but an absolute pressure transducer, that basically measures the actual pressures changing versus a baseline that it's at, whereas a delta pressure transducer only measures changes in pressure. So you won't see the graphing waveform format that we're going to be analyzing in this video on a delta pressure transducer. You would just see pulses up or pulses down, representing if there are positive or negative changes in pressure and what those volumes are, but it will only measure the change in pressure and not give you a waveform of the actual pressure over time like the absolute pressure transducer will. We'll maybe go into that a little bit later if we've got time or on the video on the paid channel, but you do want to make sure that you've got the right transducer as well. Okay, what we're going to get when we do this is you're going to get different waveforms on your scope based on the conditions with the engine, whether it's idling, which is more commonly how the waveforms are analyzed is during an engine idle. Again, that would be engine running during this test, something you won't do with your compression gauge, obviously, right? You can also do cranking as well, and the waveform will change, and we'll talk about why they look different. Another one that I like to do, especially if I suspect some type of an exhaust restriction, will be a snap throttle test. On my videos here, you know that typically what I do is I use an old vacuum gauge and I use the pressure measurement on the vacuum gauge by tapping into the exhaust and checking for back pressure. Well, in real life, so to speak, if I suspect back pressure, I actually use the transducer on the scope, and we'll overview how that would look as well. But what you're going to get basically on your scope, what we're going to see here with the transducer, on our y-axis over here, we're going to have voltage, and on the bottom x-axis here, we're going to have time. So what the pressure transducer actually does is it converts the pressures that it measures into voltages, and it's proportional. So the higher the pressure, the higher the voltage, lower the pressure, lower the voltage, and it plots that out over time to make a waveform. The waveform is going to look something like this. Of course, we will show you the actual one on the car, but let me draw this out a little bigger so that we can familiarize. So when we see it on the car, we immediately recognize what we're looking at. And very important, one of the things we're going to look at is our valve openings and closings. So I want to show good definition here. It's one of the characteristics you look at with the waveform. I typically don't really pay attention to the amplitude on the voltages or the time even. I don't really look at so much. It's the shape of the pattern that really is the most important thing. Now on a low compression thing or something, yeah, of course, you're going to look at what your actual compression measures, but you're interested in why that is happening, and that why is going to come from the shape that you see on your waveform. So the shape is really the most important thing. Okay, and there's very specific things we're going to be looking at here, so I want to make this as accurate as possible, and then we're just going to repeat this again. All right, and that'll just repeat on and on again. This is the same cylinder again and again and again, just the one cylinder. All right, so let's analyze what we've got here. We know that, hopefully if you watch this channel, you know that between here and here, that's going to be 720 degrees. We have two compression strokes here, 720 degrees apart. That's two rotations of the crankshaft to the one rotation of the camshaft, and that's what we're seeing here. So this here, we're going to call this 0 degrees, and we're going to call this 720 degrees. And what I'm going to do is segment this by every 180 degrees. That'll be every top dead center on the piston and every bottom dead center on the piston. So I'm going to draw our first line, 0 degree here, and there is also significance to this line. It's right in the center of this peak here, and the symmetry of the peak, the shape of this peak, that it is equal on this side of the center line and this side of the center line, that those are equal. That's also very important. We will discuss that. All right, so that's 0 degrees here. That's going to be top dead center compression. All right, so that means at this point, right about there, that must be where our intake valve has closed. Again, we were at bottom dead center, and now we're pushing the piston up. So previous to this, we were at bottom dead center, sucking down on the intake stroke, drawing in the air. Well, obviously, if we are now building pressure up here, and you see we're building pressure quickly over time, well, then that must mean our intake valve has closed. Our exhaust valve was already closed. So the intake valve must have closed, meaning both valves are closed, so that we're building up our compression on our compression stroke. I'm going to put a C there for compression stroke. We obviously are building up compression very nicely. Say we've got like, I don't know, 80 PSI here or whatever, and we see that during the engine running, we've got our good compression, valves are sealed, the rings are sealed, we don't have a leak through the head gasket or a crack in the block or something like that. So we've got our good compression here. Now, as we know, once the piston comes to top dead center on compression, that's going to be the peak compression, the highest voltage. So that's why our voltage is at its peak there. The pressure transducer is seeing that highest point of pressure. And then the piston starts coming back down on the power stroke after the air fuel mix is ignited by the spark plug and we pass our top dead center compression. And now that explosion happens and the power from that explosion pushes that piston down to drive the car. Well, technically, we don't actually have a power stroke here because remember, our pressure transducer is threaded in through this compression hose like this, and that is in the place of the spark plug. So we don't have a spark plug in the cylinder because our pressure gauge setup is screwed in where the spark plug would be. So that means we don't actually have a power stroke. So what this stroke is called in this application is the expansion stroke. I'm going to put an E here for expansion because the piston's coming down, so we're expanding that area in the cylinder again, but there isn't really a power stroke there. The piston's just being pulled by the crankshaft in the rotation of the engine is all that's happening. It's not being pushed down by the combustion. All right, as that comes down, the piston again is going to come to bottom dead center. Now, you would think that our bottom dead center would be right there, right? Well, it isn't. What's happening there, the change that we're seeing right here, where we're starting to build pressure up again, as a matter of fact, this line right here, I'm going to put ATM. That's for atmospheric pressure. Now, this is an absolute pressure transducer, so we could put 0 psi here if we wanted, but there actually is some atmospheric pressure there. But I'm going to draw a dotted line here representing the atmospheric pressure. And that means anything below that line, anything underneath that line is going to be vacuum events, and anything above that line is going to be pressure events. And of course, it's proportional. The more above the line, the higher the pressure, the more below the line, the stronger the vacuum. We will talk about some significance with these points here, here, and here in a second, but what's actually happening here, because at this point, we've stopped drawing vacuum now, what happened here is the exhaust valve. I'm going to put an EXV, exhaust valve, must now start to open. But that doesn't mean that that's bottom dead center for the piston. That's not how an engine works. In an engine, the exhaust valve actually starts to open a little bit before the piston gets to bottom dead center. Bottom dead center of the piston actually occurs right about there. Let me move my exhaust valve. All right, we'll move my time mark over there. Okay, this, because we were at top dead center here, and now at this location we're at bottom dead center, how many degrees of engine rotation is that? You should know that's going to be 180 degrees of engine rotation, crankshaft rotation to be specific. So this point right about here is where we reach bottom dead center. The exhaust valve we can see is opening a little bit before that. Anything over to my left is going to be earlier events or advanced events, and everything else is later or retarded. We will come into that if we have an advanced or retarded camshaft, for example, and the effects that we would see with that. All right, so exhaust valve has started to open here just before piston comes to bottom dead center. And now with the piston at bottom dead center, we know the next stage in the 4-cycle engine is that it's going to come back up again, this time pushing the exhaust gases out. And that's what we're seeing here is the exhaust gases getting pushed out. And I suppose this is a little turbulence here or something with it spinning in the cylinder as that piston is pushing the exhaust gases out. What we don't see though is we don't see pressure like with the compression stroke. Why do we not see pressure here? Because the exhaust valve is open. If the exhaust valve is open, we can't build up pressure as that piston comes up because everything's escaping out the exhaust valve, which is the whole intent, to get that exhaust cleared out. Now, we've got an E already used up for an expansion here, so I'm going to put an EX here for exhaust stroke. So there's our exhaust stroke. Now, over time, as that piston is moving up, over time, at some point, the piston reaches the very top again. So we're at top dead center of exhaust stroke. That position for top dead center of the exhaust stroke, let's see, here we've got bottom dead center, expansion stroke. Here we've got top dead center again, EX. of the exhaust stroke. That's another 180 degrees, right? So we know now that's going to be 360 degrees. There's one full rotation of the crankshaft, one full circle that it's gone, but the camshaft is only halfway done. With our piston now at the very top of the cylinder, having expelled the exhaust gases out, we notice that there's a phenomenon here. We notice that there is a big change in our cylinder pressure to convert to vacuum now. And we actually have two events that are going to happen at this time. And it is a little hard to discern them exactly where they're happening. But we have two things happening. One of them is, of course, the exhaust valve is closing. We are closing the exhaust valve because we have already expelled out the exhaust. But also at the same time that that is happening, the intake valve is starting to open. This is, you've heard this valve overlap if you're not familiar with it. And this is a phenomenon that engines have. I'm not exactly totally 100% clear on it, but it helps with the breathability of the engine. And I know on a performance engine, you will have a lot of variance with valve overlap in certain situations. Valve overlap also can be used for EGR in a variable valve timing type engine as well, instead of using a EGR valve. But whatever the case is, you're going to have some time where both the intake and the exhaust valves are open at the same time, and that's happening in this area right here. Now, here we can clearly see that we've developed our vacuum again right at that thick point with my marker right there. So what must have happened there is now we've got the intake valve open with the exhaust valve closed. And with the intake valve open, remember we were at top dead center here, so now the piston is coming down again. When it's coming down with that intake valve open, it's sucking in the air from the intake manifold, and we're going to repeat our process again. At some point, that piston is going to come down to the very bottom after drawing in that air. And that is going to be another 180 degree position, maybe right about there. That puts us at 540 degrees of crankshaft rotation with our piston at the bottom dead center at this point. Now, we've had our intake valve open here, bringing the piston down, drawing in the air. We can see right there, right at that point there, a sharp shift developing pressure now. So what must have happened here is the intake valve has closed. Well, if the intake valve is closed and the exhaust valve has been closed, we're right back where we started before. We're on the compression stroke, and we're going to build up pressure again to top dead center. So again, our piston is going up this way, building up that pressure. If we draw that center line down here, that top dead center happens, we know, 720 degrees. All right, a little bit confusing, a little bit messy, but let me clean up a little bit of this here, and I want to show you some of the points that we look at that are of particular interest on this curve. Okay, once we familiarize with that pattern, we kind of have that burned in our brain, we will quickly identify any anomalies. Now let's take a little zoomed in look. That actually would be a problem if we saw a pattern like that. I will explain shortly. We're going to analyze some things that you want to look for in the waveform. So one of the very important things that we want to see, we'll start here. We want to see what we call a symmetry. Well, I call it a symmetry in that compression peak. And that isn't very symmetrical, actually. What we want to see is this center line evenly divides that peak, so it could almost be folded perfectly in half. That symmetry is very, very important because this indicates that we aren't losing any of the volume in the cylinder during the compression, or that the valves aren't opening too early or too late. And here's another part to that that affects it, and that is if we were to draw a line here along this vacuum line, we need this point, this point, this point, which is this point, by the way, it's just happening again. We need those to be essentially the same, very little difference from that. We definitely don't want to see something, for example, like this. We want this to be on that vacuum line. The reason is because if we've drawn that air into the cylinder, so we've got, of course, here the piston was coming down, and then here we're on the compression stroke. Well, when we drew that air into the cylinder, well, on the compression stroke, we have a fixed amount of air in that cylinder, and none of it's escaping if this engine is in really good condition, right? We're not losing any of that air. So we've got that fixed volume of air that is now getting pressed up by the piston, and it's getting compressed into a little tiny volume, but the amount of air is actually still the same. Well, remember, in our application, without blowing up the cylinder and all that, we're bringing that cylinder back down. So we've got our tightly compressed air up there, and now the cylinder is coming down, so we're stretching out again, expanding that air out to the point where it was when we first started the compression stroke. So the volume of air that we've compressed starting at this point will be exactly the same volume of air that's over here. The piston is back in the same exact position, so our pressure would be exactly the same, or the vacuum would be exactly the same as before. And that's what we see here. And then after our exhaust stroke, when we start sucking the air in again, the same thing happens, and we're back at this vacuum again. This shows we aren't losing any air in our compression or during our cycling. Now, because we have that same volume of air, both as it's being compressed and as it's coming down, we're going to have another phenomenon here, and that is going to be what causes that symmetry with our curve here. And that is, what's happening is the piston is moving up at the same speed that the piston is moving down. All right? If we were to have an issue where we lose compression in the cylinder, we would see a couple of things happen. One thing we would definitely see happen is a difference in our vacuum line. So let's say we're bringing in our air, okay? But then let's say that we have some type of a issue where everything is really good, but then we open the exhaust valve too soon, all right? So here is our 0 degrees. And then let's say we had that issue that we've got the video on with that Honda, where there was a valve flash issue, and our 180 degree happened right about there. That's 180 degrees. This is bottom dead center exhaust, all right? Well, one of the things that if we really looked at that waveform a little more carefully, we would have seen is we would have seen a phenomenon a little bit like this, where this point here is not the same as here. And that's because we've got our fixed volume of air getting compressed, but then as the piston's coming down with that same volume of air, well, the exhaust valve has opened, it would have opened right there. Our exhaust valve opened much earlier than typical, because typically our bottom dead center would be around there. So we can see that we are advanced with that exhaust valve opening. Well, if that exhaust valve opens early, that air escapes out. And if that air escapes out, we're going to see that as a normalization in that cylinder to atmospheric, a lot closer to atmospheric, because we have lost that air. The air volume is not the same. Now, if it happens to be that the leak is bad enough, we will also see a shift in the center line relative to each side of that curve. So we can see here the distance is shorter than this distance here. And all the way down, this distance here is shorter than the distance from the center line here. And that's representing that because of the loss of air, we're losing that little bit of push from the compressed air in there. And that means the piston is moving a little tiny bit slower. Again, you're never going to catch this anyway other than a scope. But the piston is actually moving a little bit slower on the downstroke than it moves on the upstroke. All right? So if we see this point here and this point here are different, that is a flag that we have a mechanical issue, and that should stand out to us that we need to do some analysis on this. All right, there is another thing as well that we pay attention to, and that is this drawing is really not very representative of what we're going to see on the actual car. Let's be particular here. And actually, we really do need to be particular like that. Okay, so if we see here, we're kind of happy here. Our vacuum bottoms are pretty much in line here. But the other thing that we want to look at is here, here, here. What we're looking at is the valve openings. And what we can see is that we get very crisp, defined valve opening patterns in these specific areas. You can clearly see a definitive change in patterns here, a very definitive change. And what that means is that the valve is opening in a consistent manner. It's not clogged, it's not, there's not a worn cam lobe, there's not a roughness to the opening or something like that. Very defined valve movements is another thing that we're going to look at, and we'll very clearly be able to see those on our compression pattern when we pull it on the car. Final thing we may look at is, of course, the actual voltage measurements or pressure measurements if they're provided by your software, and making sure that we've got appropriate pressure measurements. If I see my peak pressure on the compression stroke at, say, 30 psi, well, then we clearly have a compression problem. All right? And then, of course, we're also looking for our valve timing incidences. If we see that a bottom dead center event after our expansion stroke, if that bottom dead center is occurring somewhere in the actual exhaust trace, then we know that we have either an advanced cam or an early opening exhaust valve or something like that. We would also see it with the intake as well. And as I pointed out in that video, there are some specifications we can look at where there may be, on an ideal engine, something like 43 degrees before bottom dead center, we see that valve open, and we would actually be able to measure that on the scope. So this gives you some idea of what we're going to look for in our waveforms and give you some familiarization with it. Let's go ahead now and pull an actual waveform from the vehicle, and then what we'll do is we'll see if we can pull some abnormal waveforms. I don't have an abnormal vehicle right now, but we'll see if we can just randomly pull some from like Google and see if we can analyze them. All right, kind of excited here because what we're going to do is I'm going to actually use my brand new car for this. And what's the first thing that I do? Well, I take it apart to start doing experiments on it. But what I'm thinking is, with this being brand new, we're going to have a perfect waveform on here.
Did that guy just use a power tool on a brand new car? I'd never take my car to him. He's a hack.
Yeah, I know. You go ahead with your vacuum gauge there, buddy. We'll see how well that works for you. All right, so we've threaded in our compression hose. Gonna connect up my pressure transducer here, and then we're going to hook it up to the scope. Okay, so for my settings here, you gotta play around with these sometimes. get a little more detail here. I think we're going to run a half second per division here. We can also, nice thing about picoscope, I can actually select the WPS 500. So I'm going to do probably up to the 200 PSI range. I think that should work pretty well. We also could put in another channel. Typically what I'll do is I'll put in a second channel with an ignition marker for that cylinder so I can check the ignition timing relative to the waveform analysis. We may do that a little bit later. Right now we just want to focus on the waveform. All right, let's go to the car and crank this thing. And I'm hoping this car has a crank-only mode that we can do for a second or so. Oh, it does. Beautiful. All right, now let's run it. Now the car is running terrible because we do have, of course, a misfire. So the car is not going to be running very well. Actually, I have check engine light on my brand new car. All right, now let's do a couple of snap throttles here. And that's all we need. Okay, let's stop that capture and analyze it. Okay, it looks like those settings worked really, really nice. And that's typically the settings that I start off with all the time on any car, so I'm kind of used to it anyway. Let's back up, and this would be our cranking. We can see the cranking and then the running. We see the running here looks very, 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 very similar to what I drew on the board. Let's zoom in on that a little bit. Okay, we can see that it looks very similar to what I drew on the board. What we're going to do is take a look at this waveform, but I want to show you a couple of things here. One of them is the difference with this waveform with it running versus waveform with it cranking. All right, so first of all, let's look at our running waveform here. Okay, so looking at our running waveform, we see it is very similar to what I drew on the board. We can see that we've got our intake here, we've got our exhaust stroke here, so anything below here, that's going to be vacuum. Anything above this line is pressure building. So we can see that we're at vacuum here, drawing in the air. We see we've got our compression stroke here. As a matter of fact, let me make this easier. I'm going to draw in some markers here. Now that one won't center out really. There we go. All right, so we're going to make that 0. Going to make this one here 720. And then what we're going to do is insert 4 partitions representing 720 divided by 4, which will be 180-degree segments. And now we can very easily see our piston rotation segments here. So basically what we've got is our top dead and bottom dead centers of our piston locations drawn out for us here. You'll see it's very similar to what I drew earlier. We're starting off here with our compression stroke. So you see that we've got our compression coming up and down. We then see we've got our exhaust stroke here, and then we've got our intake stroke, and then back to the compression stroke, just like I showed on the board. Now, before I show you a couple of very important details on this waveform, I want to show something that you've noticed, and that is that this looks very different than the cranking compression waveform that we saw. So let's back up a bit, and we'll come back to this. And what we're going to do here is look at our cranking waveform right here. And you'll see it's very, very different, isn't it? One of the things you notice right off is that the compression is much higher. The compression peak is much higher than with it running. That would seem counterintuitive, but we have a couple things going on with that. One of them, and I'll be honest, I'm not exactly sure why it is, but I think you have less vacuum in the engine with the cranking than you do with the engine actually running. We see less vacuum represented here, actually, which is why it looks like we don't really have an exhaust stroke here? We do, it's just not as pronounced because we have much less vacuum peaks. These would normally be way down here, so that exhaust is more accentuated, and then we would have these down here again, but we don't have that with the cranking. We have much less vacuum. The other thing, the slower engine speed, I think, also makes a difference. I wonder if I did this, well, you know what, this is a stick shift. It'd be very hard for me to do the cranking with the throttle plate all the way open, but I wonder if we would get even more compression if I cranked it with the throttle open, but I don't have 3 feet. But you'll notice the higher compression, the more flattened exhaust, and I think the less turbulence there because, again, the engine's a little bit slower, so there's more time to push that exhaust right out that exhaust valve. We've got a lot more time available. Again, this would also be very helpful if I were to put in a firing line here with a spark event to show that the spark event is happening just before top dead center on that cylinder. We could have a great way of showing ignition timing on there. Maybe we'll do that later. But I wanted to show you the difference with the cranking. The other difference you're going to notice, a big difference, there was a huge difference when I did the snap throttle. So let's jump back to the idling. Okay, and here's a pretty good capture here where the engine is starting. And then once it gets idling, we see that lower compression. We see our typical expectation like I was showing earlier. We will analyze that. But then later on, we did another variable, and we did a snap throttle, which is shown right here. Here we've got a snap throttle. So let's look at the snap throttle here, and let's see what you notice that's different. See if we can get a couple of idle events in there, and then a few snap throttle events in there like that. Okay, so you'll notice a couple things here. One of them, it's a little bit easier to see when it's zoomed out, and that is right here, we've lost our vacuum on the snap throttle. Think about, why would that be? Why would it be that we've lost our vacuum on the snap throttle? Well, if you think about it, it's because we opened the throttle plate all the way. We know that the highest vacuum is going to occur during idle because you've got that throttle plate closed and the piston's coming down. It's trying to draw that air in to fill the void, but the throttle plate is closed, so you've got high vacuum. Technically, your highest vacuum is on a deceleration. When you open that throttle plate, you now have open to atmospheric. You basically lose that vacuum, right? And that's what we're seeing right there. The other thing you'll notice here is, of course, a much more pronounced peak on our compression. And that's, of course, because we're drawing much more air into the cylinder, compressing a far greater volume, all right? So one of the things we would look for here, do you see how nice and even this line is through the snap? If we were to see this bottom line increase with the snap throttle, so this area right here, if we were to see kind of an upward trend in this area, that would be indicative that we're building pressure there. And that would be indicative of a backed up exhaust. So that's the way that I would check for a clogged catalytic converter or clogged muffler or something like that. That'd be a great test if we see that this area here doesn't maintain that nice straight line. All right, let's go back to our area of focus here. And oh, now I've changed my scaling a little bit here. We want to center. All right, now we're just about perfectly nice and centered here. All right, that's excellent. Okay, so one of the things that we also want to look at, this is very important, is this. I'm going to draw a line right there. And what we want to see, and you'll never see this totally perfect, but it should be pretty close here. What we want to see is that on this line, that the intake side, the intake stroke on this side of your compression is equivalent to just before the exhaust valve opens. Now, if we lose air, during the compression, and this could be for whatever reason. We also could lose air because of a timing issue. A valve opens too early, for example. What we would see is these would no longer be the same. We might see where this is up a little bit higher than here, or we might see where this is up a little higher than this area here. These should be the same. An example of this, and we actually saw it, I think, in my previous video where I found the timing problem. We can see here our bottom dead center is occurring right here, and the exhaust valve has opened here. One example where we would see the pressure change is I had an advanced exhaust valve. So my 180 mark, don't pay attention to the other ones, just pay attention to the 180. So my 180 mark on that car was somewhere over here, maybe not that extreme, but what's happening is this exhaust valve is opening way too early, way before we've reached bottom dead center. Well, if the exhaust valve opens too early, we lose the air out of the cylinder earlier, which means that we would return this to atmospheric pressure earlier, and we would see the shift of this part of the waveform up higher, representing that we approached atmospheric earlier because the air has escaped. We lost it. So that would be a perfect example of how you won't have balance on one side or the other. There's some other things we can look at too here. Another thing we want to look at is we can actually see some effects of the valves opening. So for example, right here, we see that there is a very sharp turn up here as that valve opens. If we had something, let's say a worn cam or something where the exhaust valve isn't opening smoothly and it's maybe taking too long to open, we would see a big rounded effect of that here. But we see that we have sharp defined openings. We can clearly see on the exhaust, very sharp defined opening. We see when the exhaust valve closes, very sharp defined closing. Okay, I want to go back to the board and I want to show you another thing that would happen. We were talking earlier about that advanced exhaust valve opening. And there is another thing that you can look for that will give you a very, very good clue if you've got a mechanical issue. And we can, I think it's going to be easier to show on the board. And you'll notice, by the way, that a lot of my focus is on the shape of the waveform, the pattern of the waveform, and I'm not even really paying attention to actual values of the voltages or the pressures. And that's that's not entirely true. If I've got a compression problem, I will notice the lower compression volume, but also more importantly, I just noticed the peak relative to where atmospheric is lower than it should be. And it's really kind of an, I hate to say an art, but it is, there is some interpretation with it for sure. Just recognizing the pattern. Case in point, let's have this here. Okay, so this is actually a little more accurate representation of what you may have with what we have another video on with an exhaust valve that opens early. It'll be a very subtle couple of differences that you may not even notice, and you certainly won't notice if you don't know to look for them. All right, so there will actually be several differences here. Let me do this. Let's do this. Let me draw this out, and then you tell me what you notice different about this waveform. All right, so let's test your knowledge here a little bit and see if you can notice the difference. So what I've done is, of course, this would be unlikely to happen, although I think we're actually going to see this happen on the car coming in this weekend. But what we've got, remember, we always have the same cylinder over and over and over again because the pressure transducer is in just that one cylinder. But what I've done is I've drawn my normal cylinder transducer waveform here and the abnormal waveform here. All right, and let's see if we can note differences with the abnormal versus the normal waveform. So if we look, one of the first things we notice, at least that I notice, is right here. There is a pressure bump in that exhaust stroke where there shouldn't be. If the exhaust valve is open and the piston's coming up to top dead center and it's pushing all that exhaust out, there should never be any pressure there. Now, one explanation you may think is, well, maybe there's indication that there's exhaust back pressure from a clogged catalytic converter, a clogged muffler. Well, there's other clues on here that indicate that that's probably not why that's happening. What is probably happening is if we look right over here, this 180-degree line representing bottom dead center of the power stroke, well, actually the expansion stroke, is happening too late. So what happened, if that is happening too late, the exhaust valve right here opened too early. If the exhaust valve opened too early, it is also going to close too early. So what happened here is the exhaust valve closed too early. Well, if the exhaust valve closed too early, then we have both valves closed for just a brief period of time during a stroke to expel the exhaust. So it essentially creates a little bit of a compression on there, like a compression stroke. And that's what we're seeing here, is seeing a little bit of that exhaust gas that's being compressed just for a brief period of time because the exhaust valve closed too early. Then our intake valve opens and we see that we return, back to normal then. But that's what happened there. Now there's another thing that we notice too, and that is if we have our line at our vacuum, we see on our good cylinder here that all these points are essentially the same amount of vacuum, whereas here we have a big delta. The reason for this is because, of course, if the valve opened early, we no longer have the same contents of the cylinder on the upward stroke as we do on the downward stroke, right? We've lost some of those contents, so we return to an atmospheric condition a little bit quicker. There's another thing I tried to draw. See if you notice it here. Do you notice anything different with this peak versus this peak? And if you notice, our center line through the peak shows that the peak is kind of leaning a little bit off the center line. Here we have perfect distancing at any point between this center line and any point across from the center line on either side of our peak, because the piston is going up the same rate it's going down. And maybe we wouldn't have seen this in the previous waveform so much, but what I'm drawing here is the effect that because we have a different volume on this side of the cylinder than this side, the cylinder is moving up, but it's coming down at a slower rate because you don't have that assistance with the compression pushing that piston down as much. So you notice a very slightly slower descent of the piston coming down than there was on the ascent, which is a clue that you've lost volume in the cylinder. All right, I think what we're going to do is I may pause the video here. Maybe we'll do another part to this. We're also, of course, going to cover it on the pay channel a little bit more when we get this mystery vehicle come in that really appears. There is nothing wrong with it, but there most definitely is. It has a single cylinder misfire code consistently. You can feel it with acceleration. It's not ignition. It feels like a secondary ignition, but it isn't. But we're going to be able to solve that mystery. What I think we're going to do is let's head over to the computer one more time and let's pull up just some random waveforms, just kind of test your knowledge here and have this sink in. And we'll just pull some random waveforms off Google and see if we can find anything abnormal. You can see you can get some pressure transducers fairly inexpensive. I think this is totally worth the investment. One thing this has allowed me to do is to charge more premiums on some of my diagnostics, which we will talk about at another time. I actually had a little discussion with my friend Scanner Danner, Paul Danner. We talked on the phone for quite a bit. And I will admit he has changed my philosophy on my doing the free diagnostics that I used to do. I've actually since changed that policy. And also not only that, but there are some cases where I will charge premium for diagnostics. I literally had a guy offer me $500 if I could tell him what is wrong with his car, because he had spent thousands of dollars not being able to fix it himself and at various shops and everything. So to him, $500 is a bargain. Yeah, I will gladly take $500 if you want me to diagnose your car, but you have to be able to do it. You can't just be some hack with your vacuum gauge going, oh, I can tell by ear that that's going to be a timing problem. Okay, it's not a timing problem, all right? You have to know, you have to be able to diagnose it. And technology like this allows you to do that when other people can't. You can demand a higher market for that. That's a free market economy. All right, let's take a look at any of these. Let's see if we can find any that look abnormal. Let's just take a look at this one right here. That looks pretty normal, doesn't it? That looks almost exactly like what I just pulled from the car just a second ago, doesn't it? Do we see? Now, one of the things without our lines showing the top and bottom dead centers of the cylinders, we can't tell if there is a timing problem here or not, but we can easily see that that looks pretty normal. I don't see anything abnormal with that. Right here, we just so happen to have a division of the screen on the Pico, a time division right through the center of that peak, and we can see that that peak is very, very balanced too. All right, so we're going to search in-cylinder abnormal pressure transducer waveform. Let's see if we can catch something abnormal looking here. Oh, there's still a lot of normal ones. That one, that one's not abnormal because we don't have the completion over here. And over here we can see that the vacuum is the same there and there. We've got good valve openings, symmetrical peaks. So thought maybe we had a little bit lower vacuum here than here, but it's just not complete. But you can develop an eye and you can sort of spot these problems pretty easily. There's a problem right there, if I've ever seen one, right there. Let's take a look at this one, because do you see what I'm seeing on this one? That is, this exhaust pattern here is absolutely horrific. Right there, absolutely horrific. Let's see what's going on with that. This is on Auto Nerds. I believe I've heard, oh, it's a chat room. Well, that's a hell of a chat room, by the way, if they're talking about this stuff almost 17 years ago, too. I guess this has been around for a while. Holy cow, these are Auto Nerds. 17 years ago, I wasn't even working on cars. Wow, look at these guys. Well, I don't want to read through all this, but let's go ahead and let's take a look and see if we can figure out what maybe happened there. So we see that we've got what looks to be good intake, good valve opening. We've got, well, I was going to say, what is that? It literally says, what is that? It looks like we must have lost some compression here. And then look how wide this downstroke is becoming. And then here is exhaust valve opening. I agree with that. We're trying to get that exhaust out, but it looks like we've already lost it. Then the exhaust valve closes. What would be really nice to see right now would be what this actual pressure is on the compression, and we don't have that. That would be very helpful to see. But it is very obvious that there is some issue here. I don't think we've got the data, because I would like to see what's happening with that compression pressure. Another thing that would have been nice is we've got 0 degrees here, we've got 155. It would be nice to see, I guess we could calculate it out, where the 180 is, where the 270 is, and see maybe this could be a timing issue, possibly a timing problem there. Yeah, we just don't really have the data on this one, but we would know what data to get now, don't we? All right, well, as you can see, I am still clearly learning a lot of this myself still, and I really only have been doing this since that video where I recently got the pressure transducer at that time to diagnose that Honda, and it's paid for itself many times over ever since. But there's just so many variables and things to consider, so many different things that can happen with an engine, and I've only seen so many of these waveforms. But you can clearly see once you get the understanding of this, yeah, you can easily identify that there is an issue. Keep in mind that this also is not like a primary immediate go-to for me now that I've got this technology and I'm learning it. It's very inconvenient for the most part to use this, just as it would be with a compression test. You can't just do a in-cylinder transducer on a car without having access to that cylinder. So you still run into the issue if the car has that cylinder of interest under the intake manifold. Well, you want to use other methods first and see if you can determine justifying an issue, because you don't want to remove an intake manifold just to do a cylinder pressure transducer and find out that it's an ignition problem or something, for example. So you just want to keep in mind, this isn't the end all be all for diagnostics. It's got its ups and downs, just like every other procedure. All right, well, I hope you found this very educational. For you guys over on my paid channel at www.schrodingersboxqm.com, I will be attacking that mystery truck this weekend. We're gonna put these concepts into application and try to figure out what nobody else has been able to do on why that truck has a misfire. So I look forward to seeing you guys this weekend.